Welcome, friends, to our next installment of thermochemistry. This is new compared to what you learned last year, dealing with Hess's law. So basically, Hess's law is pretty straightforward. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So it still has a beginning and an end. There's still an overall change in heat, which is a state function. However, if it happens, as I said, in a single step or a series of steps, all those individual steps have to ultimately add up to the change from beginning to end. So for this one, as you see, a little diagram, A plus 2B has an increase in heat, and then C going down to 2D has a loss of energy, delta H2, and then the overall delta H of A plus 2B going to 2D is just them added together, where H1 is going to be positive, H2 is going to be negative, and you get your overall delta H of the process. Another way of looking at the exact same thing is you still have reactants going to products. It could go in just one step or multiple steps. Either way, the beginning and the ending are still the same. So our relationships involving heat of the reaction, College Board added the subscript RxN all over the place, dealing with thermodynamics. So just kind of get used to that. Does it need to be part of your answer as part of your units? No, it does not, but you're going to see it a lot. So a couple things, when you're dealing with these reactions, if you multiply the reaction by some factor, you have to multiply delta H by the exact same factor. We're going to see an example coming up. Again, delta H is an extensive property, depends on how much you got. So for example, if we take the combustion of carbon to make carbon dioxide, it is that amount in kilojoules, but if I multiply the whole reaction by 2, then the amount of delta H should also double in that sense. If you reverse a reaction, then the algebraic sign has to be reversed also. So if it's normally in the forward direction, an exothermic reaction, if I reverse it, I'm looking at it in the reverse direction. It now is an endothermic process. So like the above one, if I go carbon dioxide decomposes into carbon and oxygen, which should not obviously happen under ordinary circumstances, it should be an endothermic process as indicated by the positive delta H. Remember, negative delta H is exothermic or a release in energy, positive delta H endothermic or the absorption of energy. All right, standard conditions. Biggest thing with thermodynamics, thermochemistry, is there are set conditions that must be met in order for you to be considered standard conditions. So the standard state is a state of which material is defined by these set of conditions. Gases are exactly at 1 atmosphere of pressure. Pure solids and liquids in its most stable form, usually at 1 atmosphere of pressure and a certain temperature, which is usually 25 degrees Celsius. So our standard temperature is 25. If you remember from gas laws last year, standard temperature and pressure, STP, is 0 degrees Celsius. Now, STP is specific to gases only. When you're dealing with solids and liquids, you're at 25 degrees Celsius. So we don't want to mistake those two things. Substances in a solution tend to be 1 molar solutions. If it's not 1 molar, which is going to play more of a role, we get to electrochemistry, then things are going to be affected. So the standard enthalpy change, notice it's delta H naught. That little, looks like a degree symbol after the H is called the naught symbol. When you see the naught symbol, we are talking specifically about standard conditions. So 25 degrees Celsius, 1 atmosphere, 1 molar, things of that nature. So standard enthalpy change is the enthalpy change when all reactants and products are in their standard states. When you use the appendix of your book or in one of the reference sheets that you'll be able to print out or look online, has a bunch of values listed for you. They are at standard conditions. Standard enthalpy of formation. So it just adds a little subscript of an F. We're still dealing with delta H. Now, delta H, again, refers to a process. So at the end of the day, it's the same idea. The subscript just tells you the type of process that's going on. So in the enthalpy change for the formation of 1 mole of a pure compound from its constituent elements, you'll have to be able to identify a formation reaction. You'll probably have to be able to write a formation reaction. The stipulations, your product can only be 1 mole. So the coefficient on your product must be 1. Therefore, coefficients in your reactants can be any number it needs to be, any fraction it needs to be in order for it to actually work out. And then secondly, it has to be made from individual elements. Elements need to be in their standard states. So if you're using any of the diatomics, most of your diatomics are gases. There's 1 liquid. So you've got to be aware of that one. So states do matter. When you're talking about reactions, the states are going to play a role. So make sure you pay attention to them. The delta H for a pure element in its standard state is 0. So when you're trying to write the reaction, you write the reaction. When you go to solve the problem and you're looking for a number that you need, if it's an element in its elemental state, so oxygen, O2 as a gas, the formation of O2 as a gas has 0 delta H of formation because it exists naturally. It is just there. All right, so a couple examples we'll look at. Here's the combustion of methane. Methane plus oxygen gives you CO2, H2O. Here's one similar graphic to the one we first saw with Hess's law. So we can see that methane and oxygen with the purple line are producing carbon dioxide and water. It has a delta H of the reaction of minus 802.5 kilojoules. Or you could look at the decomposition of methane turning into carbon and hydrogen gas. Oxygen stays the same. Then you could look at the formation of carbon dioxide and the formation of water. So kind of 3 steps, if you will. Add all of those things up and you're still going to get the same answer. So we know this one to be true as given by the chart. All I'm going to do is, sorry. So next one is the combustion of carbon as graphite, as written as 2A from the above. And then here is the formation of water from above. I know the numbers don't match. Not too sure why that happened. Sorry about that. But notice in the 3 reactions written on the left-hand side of the screen, all of the products are 1 mole. The left reactants can have any coefficient they want, but the products have to be 1 mole. So if we take this number, we know decomposition, that's fine, forward direction, algebraic sign stays the same. Here's graphite being combusted to carbon dioxide, again, negative 393.5. And then here is the combustion of hydrogen to make water. Now the number matches. Yay for me to finally do that. Everything crosses out, but what is left over, the reactions, when you add up individual reactions in Hess's law, they have to add up to the overall reaction so it matches the very top of the screen. You add up all your numbers, and you should get the exact same answer. So 2 things to verify. 1, the reaction gets added up to equal the overall reaction given, which it has to do that, and then add up your delta H's. Here's another example. Let's have you do this on your own. So you can pause the video or keep it going. All right, here we have, sorry. So here's the answer. As you can know, should have gotten C as your answer. Any questions? All right, here's a fun one. I'm gonna pause my recording so it will look like it goes pretty quick, but you can pause yours and do this problem. All right, we should have paused the recording. You've done your answer, and we'll see what we get. All right, answer should be E, or -11. So in the first reaction, we reversed it. That's why the arrow is yellow, and we multiplied by 1/6. The second reaction, we did not reverse it, left it alone, but multiplied by 1/2. And the third reaction, we reversed it. That's why the yellow arrow, and multiplied by 1/3. Notice same multiplication on the delta H values, and then change the algebraic signs. So it was a -47, now it's +47. And in reaction number 3, it was +19, now it's a -19. When you multiply through, add it up, you should get -11. So not all problems are going to be this kind of crazy with fractions. Usually it's going to be whole numbers or a 1/2. But the idea is still the same of multiplying by some factor to make everything work out and match the overall reaction above. Thank you.